Welcome to Whole Body Vibration Exposure in Construction, examining acute effects, guidelines, and risk mitigation strategies to prevent MSD and injuries. We're glad you're here. My name is Yusra Benjeloun, Administrative Coordinator and Projects Manager with the Work Wellness and Disability Prevention Institute, and I'll be co-moderating today's webinar. This webinar is made possible through the support of the Community Game Grant Program through the BC government, as well as donations and memberships to WWDPI. We thank our program partners, Canadian Council on Rehabilitation and Work, Education Advisory Committee, and speakers who contribute to this webinar series. While we're waiting for others to join us, I'll go over a few technical points for the webinar. You should be able to hear the presentation through your computer speakers or through the conference call line if you dialed in. Please use the question box to submit any issues you may be experiencing and to ask any questions you have related to the presentation. We will be collecting questions submitted throughout the presentation and follow the presentation with a Q&A based on the questions submitted. Following the webinar, any questions not answered in the allotted time will be answered and distributed after the event. The presentation will be recorded and posted for free on our website within a week, along with the slides. You will be emailed the direct links for all of these items when they're available. Today's webinar will be co-moderated by Dr. Philip Bigelow, who will introduce our presenters and run the Q&A session. Dr. Philip Bigelow is an associate professor in the School of Public Health and Health Systems at the University of Waterloo and has a background in occupational epidemiology. And now I will hand it over to Philip.
Thank you, Yusra. So Phil Bigelow here from the University of Waterloo. So our presenters today, it's really a great pleasure and honor to introduce them in the webinar. Marcus Young will be going first. Marcus is currently a postdoctoral research associate in the Division of General Medical Sciences at Washington University School of Medicine in St. Louis, Missouri. His research interest centers around the etiology of work-related musculoskeletal disorders and development of prevention strategies and interventions to mitigate injury risk. He has expertise in lab and field-based human performance measurement and knowledge and exposure estimation using population-level data. He obtained degrees from Simon Fraser University in British Columbia and his PhD from the University of Waterloo. So Bronson Dew will be going second in the presentation. Bronson is a research project coordinator at the Center for Research Expertise for the Prevention of Musculoskeletal Disorders, better known as CRE-MSD. He obtained a MSc in Public Health and Health Systems along with a BSc in Kinesiology from the University of Waterloo. His master's thesis topic was on the impacts of whole body vibration exposure on drivers' vigilance and discomfort. So his current research focus is on helping inform standards to prevent and manage work disability in the paramedic sector. So thanks to both Bronson and Marcus, and I'll let Marcus take on the first session. Thanks, you guys.
Great. Thank you, Dr. Bigelow. So Bronson and I would like to thank WWDPI and CREMSD for the opportunity to discuss some of our research on whole body vibration. So whole body vibration is the ubiquitous physical exposure in many industries and is common in daily work, and not only in construction, but also in agriculture, mining, and transportation. So the focus of this presentation is on the exposure itself. And we will provide examples from the effects of vibration in both the transportation industry and by simulating vibration from agricultural machinery. We hope that our discussion might generate better awareness and also spur ideas when reflecting on this physical exposure in construction work. So the goals of today's webinar are to examine the acute effects of whole body vibration, investigate whether established occupational guidelines protect the worker from possible injurious short-term effects, and also offer considerations to mitigate adverse vibration effects. We will discuss the results from two studies, a naturalistic study on vibration exposure and the effects on cognition over a workday and over multiple workdays, as well as a well-controlled laboratory study on the acute effects of vibration at distinct intensities equivalent to current guideline thresholds. So what is whole body vibration? So whole body vibration are the shakes, bumps, and jolts that are transmitted from the vehicle to the occupant You might have heard of the possible benefits of vibration used for exercise and rehabilitation. But on the other hand, there is strong epidemiological evidence that demonstrates the possible adverse health effects of vibration in occupation. So what differentiates whole body vibration intended for training with that from occupational exposure? One is the route of transmission, where vibration for training is usually through the feet, whereas in occupation, vibration is usually transmitted through the base of the spine. Another is the duration of exposure, where vibration for training might last a few minutes, whereas in occupation, it might last a few hours in a typical working day. There are also differences in the vibrational frequency, where we find that in training, frequencies are typically higher, whereas in occupation, frequencies are predominantly within the range associated with the resonance of body parts. There are also possible differences in intensities as well as the direction of transmission. So just to demonstrate the ranges of occupational vibration from different types of machinery, on the left we have some examples of vibration magnitudes standardized to an 8-hour working day. And this is from the EU Good Practice Guide in 2006. What we find here is that vibration magnitudes for common machines all fall within a similar range. We also observe to the right the levels of exposures experienced by operators of heavy equipment in the construction industry. The authors of this study found that more than 50% of 67 operators were exposed to levels of vibration that were above the standards of health risks. So the main takeaway from this slide is that whole body vibration exposure among heavy machinery operators in construction often exceed current guideline thresholds. And vibration exposure from different types of machinery in different industries generally fall within a range of vibration magnitudes. So at this time, I'll be turning over the presentation to Bronson, who will discuss some findings from his exposure assessment study among long-haul truck drivers. The exposures among this population are within, but also on the lower range of common machinery and transport systems.
Thanks, Marcus. Before I talk about my study, I just want to first talk about some health problems associated with whole body vibration. So exposure to whole body vibration may affect the body in many ways, physiologically and biomechanically. It affects the sensory motor, cardiovascular, respiratory, and central nervous systems. And these can result in long-term health problems like neck pain, hearing loss, GI problems, spinal degeneration, and low back pain. And of all these associated health problems, low back pain has been the most commonly studied. There's strong evidence linking whole body vibration and low back pain as a causal or mediating factor. Dose-response relationships have been shown between the exposure to whole body vibration and driving-related low back pain. So whole body vibration particularly affects the low back because the dominant frequencies of, say, driving a forklift or a truck, well, these dominant frequencies are similar to the resonating frequencies of the spine. And this amplified vibrational energy can lead to an accumulation of microfractures at the end plates of the vertebrates or the degeneration of vertebral discs. And this changes the mechanics of the spine, making it easier to pinch or strain a nerve or a tissue. Secondly, whole body vibration reduces the amount of nutrients needed to the spine. For one, vibration increases the amount of muscle activity needed to stabilize the body, and this constricts blood vessels needed to deliver nutrients to the spine. Also, the prolonged sitting that's often associated with operating heavy machinery compresses the discs and pushes the nutrients out of the discs. And this reduces the ability for the disc to repair. And all this is further aggravated by vibration. One more thing, vibration can desensitize the neuromotor system. As a result of this, people tend to sit with more spinal flexion without knowing it. And we know that increased spinal flexion can lead to low back problems. So prolonged exposure to whole body vibration and the sitting that's often associated with it acts on the spine in many problematic ways. And low back pain can have some downstream consequences like sleep disturbances and reduced sleep quality. There are systematic reviews and meta-analyses that have shown that people with low back pain generally have more sleep disturbances, reduced total sleep time, increased number of awakenings, and increased time spent awake after initial sleep onset. And this is a bidirectional relationship. So you could get less sleep because of pain, or you don't get enough sleep, and you become more sensitive to pain. So just to recap, whole body vibration increases the risk of low back pain via the various mechanisms that we've talked about, which increases the likelihood of having more sleep disturbances, which ultimately could affect how alert you may be at work. And so being alert on the job is particularly important for people operating heavy machinery. But more so lately, instead of this long pathway of how whole body vibration may affect alertness, some lab studies have seen acute and perhaps more direct effects of whole body vibration on alertness. So lab studies using instrumented measures found decreases in wakefulness after acute exposures to whole body vibration, and that was using EEGs. And another study found increases in reaction times and vigilance lapses after acute exposure. Lab studies using self-reports, however, had conflicting results. So why do we care about whole body vibration and alertness? Well, now I'll give you the example with the trucking industry. So driving while fatigued is dangerous for the drivers themselves and for everyone who shares the road, but it's commonly done in the trucking industry. Just under 50% of drivers have fallen asleep behind the wheel at some point, and 25% had done so in the past year, and that was a study by McCarthy et al. And another study found that over 50% were tired at least some of the time while driving, and 32% had driven with their eyes closed. So what I'm trying to say is the prevalence of fatigue in the trucking industry is high. And this is problematic. In Canada, driver fatigue is responsible for about 750 collisions per year, or 2 a day. So, and these cost a lot of money. The US DOT, Department of Transportation, says that a collision averages between $18,000 to $7.2 million, depending on the severity of the collision. And that's in USD. Now, these statistics are based on police reports, which only consider extreme cases of drowsiness. So for an incident to be categorized as fatigue related, there has to be no signs of skid marks, no maintenance issues with the truck, and good weather conditions with clear visibility. So this statistic is just the tip of the iceberg and doesn't account for any fatigue related near misses that go unreported. And I know we can't blame whole body vibration for everything. There's many factors that affect driver fatigue. So there are driver factors such as time of day, sleep duration, their health, lifestyle, caffeine intake. And there are health and wellness programs for drivers to help build healthier behaviors. There are also operational factors such as task complexity and monotony, rotational shift work, and the workplace culture. And an example of an operational intervention to improve driver alertness would be laws that regulate how many hours a driver can drive and be on duty per day and week. And finally, there are environmental factors like weather, road conditions, cab design, and vibration. So I acknowledge there are many factors that affect driver alertness, but my study mainly looked at vibration. And the reason why we're doing this is because just very recently, electromagnetically active vibration canceling truck seats became commercially available. And these seats greatly reduce drivers' exposure to vibration compared to the conventional seats that use passive air suspension. So the clip I'm about to show you demonstrates a side-by-side comparison between the conventional passive air suspension seat and the vibration canceling seat. There it goes. So in the beginning, both seats are vibrating at the same frequencies and intensity, but once you turn on the active vibration canceling, you can see that the person in the front, their shoulder stabilizes more, and there's less vibration here as opposed to the back. So that's pretty neat stuff, and there's been a lot of interest in how this new ability to reduce whole body vibration and what this could mean. So trucking companies wanted to improve their workplace health and safety culture. Drivers wanted a more comfortable work environment, and the seat manufacturers wanted a new selling point to how this technology not only benefits the driver's health, but for public road safety as well. So the objective of this study was to determine if the vibration canceling seat intervention affects vigilance over the course of a workday and a work week, and to determine if the drivers found the vibration canceling seat comfortable. To fulfill the purpose of the study, we worked with the seat manufacturer and a trucking company to help us recruit drivers who had never driven with the vibration canceling seat before. So we recruited 5 drivers to participate in a repeated measures crossover design, and we measured drivers' vigilance and discomfort immediately before and after their shift for 2 weeks. The first week was to collect a baseline measurement of the drivers in their existing seat, and then we switched out their old seats and installed the new seats, the vibration canceling seat, and we repeated the measures for the second week of data collection. So overall, we measured 50 work days pre and post of vigilance and discomfort, and we also measured the seat and floor vibration exposures for the drivers in both seating conditions. All right, so just to recap, the independent variables of this study were the 2 different seat types, the existing passive air suspension seats, which were already found in the driver's truck, and the vibration canceling seat that was installed afterwards. Time was also a factor. We looked at changes over the course of a work day and over the course of a work week. All right, so dependent variables, things that we measured. Well, we measured, as we said, whole body vibration, and this was done using a triaxial accelerometer that was placed on the seat and on the floor, and we took measurements of the A8, so and we calculated that using the dominant frequencies. To measure driver vigilance, we used the psychomotor vigilance task, which is a 10-minute sustained reaction time task where a stimulus would appear on the screen randomly between 2 and 10 seconds, every 2 and 10 seconds. And the driver would have to respond to it as quickly as possible. So in that 10 minutes, we get a total of 80 responses. And from that, we can calculate the mean response times, fastest 10 and slowest 10% reaction times, variability of the reaction times, the reaction speed, and the number of lapses, which is characterized by any reaction times greater than 500 milliseconds. To measure discomfort, we used a 10-point pain scale, where 0 is no pain at all, and 10 is the most pain you could imagine. And we used the scale for 8 different body parts. All right, so some of the demographics of the participants I just wanted to point out. The mean age of our participants was 54 and ranged between 43 and 64. And that's representative of the trucking industry, as there are less younger drivers entering the workforce. The BMI ranged between 27, which is categorized as overweight, to 44.6, which is classified as class 3 obese, which is also representative of the trucking population. They all have at least 16 years of experience in the trucking industry and worked about 45 to 65 hours per week, where about 90% was spent driving. This table just shows that the driver's lifestyle and work remain consistent between both work weeks. So sleep duration ranged from 6.5 hours to 8 hours of sleep, with a similar mean and similar standard deviation. And the time spent driving and the distance the drivers drove were similar as well. Caffeine intake also remained similar between the 2 weeks, or the 2 seating conditions. Okay, so let's look at some whole body vibration measurements. So on the y-axis, we have the intensity of the vibration measured in A8. And on the x, we have the floor existing and vibration canceling seat measurements. So for the vibration levels at the floor, you can see that it was just above the exposure action value. And the existing passive suspension seat shown here these seats were able to reduce the floor vibration levels by about 8%, getting the vibration exposures just below the action value. And the vibration canceling seats shown here significantly reduced the floor exposure levels by about 55%. And this brings the exposure levels to about half of the action value. So we successfully manipulated whole body vibration in the field while controlling for individual differences, cab design, and the workplace culture. So let's see what it does to vigilance over the course of a workday now. Just to quickly navigate this figure, on the y-axis we have response times in milliseconds. On the horizontal axis we have time of day, so pre-shift and post-shift. The black line represents the existing seat and the blue represents the vibration canceling seat. And so what we see here is that the mean reaction time is slower at the end of the day. But with the vibration canceling seat, the mean reaction time did not slow down as much as the air suspension seat. And we also saw this for the fastest 10% of reaction times. Similar trends were seen for the other PVT metrics, but not significant. So it's important to point out that our driver participants had a regular schedule and were not sleep deprived. And so this makes sense that we only saw significant differences in the PVT metrics that looked at peak performance, like the fastest 10% reaction times. All right, so changes in PVT over the work week. So similar charts, except on the horizontal axis now, it's day of work week. What we see here is that on day 1, after a weekend, the mean reaction times and the mean reaction speeds were the same. But on day 2, for the existing seat, there is an increase in reaction times, mean reaction times, and a decrease in reaction speed. And it remained there for the rest of the week. Whereas in the vibration canceling seat, it was pretty consistent throughout the entire week. So perhaps one night is not enough time to recover from the higher vibration levels of the existing seat. From the pain and discomfort survey, we saw increases in pain in the low back and the wrist and forearms over the course of a workday in the existing seat, but not in the vibration canceling seat. And we had kind of expected this to see this in the low back. That makes sense from what we talked about earlier. But the wrist and forearms was a surprise to us. And we think that the increases in wrist and forearm pain were from needing to hold onto the steering wheel tighter to stabilize the body when the vibration levels were higher. So just to summarize, the seating intervention that reduced whole body vibration to about half of the exposure action value found that there were reductions in the decrements of PVT performance over a workday, and that was seen in the fastest 10% and mean reaction times. There were some reductions in the decrements of PVT performance over the work week, and that was a trend seen in the reaction speed and mean reaction times. And there was also a reduction in the development of discomfort in the low back and wrist and forearms over a workday. So today's take-home message from the study is that there were benefits to further reducing whole body vibration below the exposure action value. We did another study in Chilliwack, British Columbia, similar study to look at different seats and its effects on vigilance. This study, we recruited 11 drivers. They drove for 11 hours per shift. Mean age was also similar. And the seating, the vibration exposures between the two seats were also similar. And we got similar results in the mean reaction times and fastest 10% reaction times. And that was this was just presented at the 7th American Conference on Human Vibration just this July. Okay. So there are some limitations to this study. But first, I just want to say this was the first study of its kind to manipulate whole body vibration in the field and look at its effect on vigilance over the course of a workday and work week. And since it was a within subject crossover study, individual factors like general health and lifestyle habits, operational factors like schedules, the routes they took and their duties, and the environmental factors like cab design were similar, if not identical, between the two seating conditions. But there are some limitations, and we'll get to that. So it was a low sample size of 5, but we were able to see significant differences in this study, and we were able to repeat and get similar findings in another area. The PVT could not be assessed while driving, and so we missed the fluctuations of alertness throughout the shift. So what we get from the PVT is a cumulative effects of vibration at the end of the day. And there were no randomization or blinding of the conditions, but that was really logistically difficult to do in the field, and this also means that controlled lab studies are very important to conduct as well. So I'm going to turn it over to Marcus now, and he's going to talk about his lab studies.
Great. Thanks, Bronson. So as Bronson alluded to, there are many known long-term health consequences of whole body vibration exposure, as well as potential short-term effects. Fortunately, when it comes to long-term health outcomes, there are international guidelines and standards that not only provide a form of risk assessment, but also provide consistency in measurement and evaluation of our acceleration signals. There are some guidelines and standards that are available to us, those being the British Standard in 1987, which considers a frequency range between 0.5 and 80 hertz. The International Organization for Standardization, both the -1 and -5, the -1 evaluates the risk of vibration relative to a health guidance caution zone. The -5 provides guidance on the assessment of vibration containing mechanical shocks. In 2002, the European Union developed a physical agents directive that sets standards for the control of vibration. So the focus of our presentation is on the EU directive. And the EU directive describes two threshold values, the exposure action value, or the EAV, and the exposure limit value, or the ELV. So the guidance indicates that if the EAV is exceeded, the employer shall establish and implement a program to reduce this value to a minimum exposure. The 8-hour reference period for the EAV is 0.5 meters per second squared. For the exposure limit value, if this value is exceeded, the employer shall take immediate action to reduce this exposure below this value. The 8-hour reference period for the ELV is 1.15 meters per second squared. The EU directive also considers mechanical shocks, which are transient forces that are of short duration and high amplitude. Mechanical shocks are also defined as vibrations that have crest factors greater than 9. And this is the ratio of the highest impact magnitude to the weighted root mean square. The equivalent EAV and ELV for vibration containing mechanical shock are 9.1 root mean quad and 21 root mean quad respectively. However, when it comes to potential acute effects, unfortunately there are no current guidelines to address these potential issues. And there are several gaps in applying existing knowledge of these possible effects into the development of guidelines. First, a lot of these acute effects are derived from exposures due to deterministic oscillatory motion, so essentially sinusoidal waveforms. When in occupation, vibration is stochastic in nature. And this really speaks volumes to the occupational relevancy of these vibration effects when a lot of these acute effects, again, have been derived from exposures intended for exercise and rehabilitation purposes. As the name implies, whole body vibration involves multiple systems and multiple domains. And it's really the interaction of these multiple systems and multiple domains that might lead to deficits in performance. And although we have nice studies like Bronson's focusing on vibration in the field, we really need laboratory-controlled experimental studies to really tease out these exposure-response relationships. So the objective of this study was to investigate the effect of 60 minutes of vibration exposure at 4 different vibration intensities equivalent to guideline threshold values. So this is a pre versus post examination. And also to determine whether there are differences in the effects between these intensities based off of the EU directive guidelines. So we recruited 18 healthy participants, 9 males, 9 females, to perform 4 conditions on 4 separate days, at least 24 hours apart. The conditions themselves were randomized on a per participant basis. We simulated signals based on field data from all-terrain vehicle or ATV agricultural herding work and fed this into a 6 degree of freedom hexapod platform. Among this population in which we collected these signals from, the estimated total daily vibration exposure duration was 2.43 hours. So we standardized our values to 2.43 hours. In terms of continuous exposure, that usually lasted between 30 minutes to 60 minutes. We recorded acceleration signals at the CPAD, and to ensure that the exposures at the CPAD were equivalent to our targeted intensity levels, we weight adjusted our input signals. So here's our 4 conditions. Our control condition, which we asked participants to sit quietly on the all-terrain vehicle setup while watching standardized TV programming for 60 minutes. A low condition, which was based off of the exposure action value with the resultant acceleration shown here. The mechanical shock condition, where we superimposed transient impacts above our EAV or our low condition at 1-minute intervals, leading to a crest factor of 10.46 and the vibration dose value of 13.49 root mean quad. And a high condition, which was based off of the exposure limit value with the resultant acceleration shown here. For all 4 conditions, they all lasted 60 minutes and we provided standardized TV programming to mitigate boredom, as well as noise cancellation headphones to reduce unwanted ambient noise. We instructed participants to place their hands on the handlebars with their feet on the platform surface, and the predominant frequency along the vertical axis was 5 Hz. We recorded a test battery before and after each condition, and this test battery consisted of 9 cognitive and sensory motor measures. Just to provide a detailed example, we asked participants to rate their perceived headache and discomfort using a 10 centimeter visual analog scale. Here the anchor points were no discomfort to maximal discomfort, and this score was later expressed as a rating between 0 and 100. So along our horizontal axis, we have our 4 conditions: control, low, shock, and high. Along the vertical axis is our dependent measure, so in this case, visual analog scale rating between 0 and 100. The black bar represents our precondition value, and the gray bar represents the post-condition value. For comparisons between pre and post, we either ran a paired t-test or a Wilcoxon rank test for non-parametric measures. To compare between conditions, we normalized our post value to the pre value and used this normalized value as the dependent measure in a linear mixed model repeated measures analysis with 2 key Kramer post hoc tests. What we observe here in terms of rating of headache and discomfort, that participants here after the low condition and high condition reported significantly higher headache and discomfort. However, across conditions, there were no statistically significant differences. So this radar graph shows the normalized responses from baseline for all of the conditions, so all of the cognitive and sensory measures for each condition. So the conditions themselves are represented by the different colored lines. So where red is the normalized post value for the control condition, green is the normalized post value for the low condition, pink is the shock condition, and blue is the high condition. The black line in the center of the radar graph is the baseline for all measures for all conditions. Therefore, this value lies around the value of 1. Any value away from the baseline signifies an increase in value after 60 minutes of exposure of that condition. So for instance, using our rating of perceived headache and discomfort example from the previous slide, we find that the high condition led to the greatest pre-post difference, followed by the low condition. We indicate here on the top right-hand corner that the pre-post differences were significant for both low and high conditions. So in general, we found that the high condition led to the greatest pre-post difference, and some of these measures were statistically significant. And this includes deficits in vigilance based on reaction time and number of errors, and postural sway in the anterior-posterior direction. When comparing between conditions, we did not find statistically significant differences. We can also examine the effect of vibration on perceived body discomfort using Borg's RPE scale. Again, each spoke of the radar graph represents a measure, in this case, a body location. Each line represents a condition. Generally, we found that in all body locations, there was a significant pre-post increase of the upper body in all conditions, where in the high condition, in general, this led to the higher pre-post condition response or difference. With increasing vibration intensity, we found larger and significant pre-post discomfort ratings involving lower body locations. So just to summarize, we observed upper body discomfort in our control condition without vibration. In our low condition, we found upper body discomfort, increases in headache and discomfort, postural imbalance, but the effect on cognitive functioning was less clear. And this was due to some discrepancies between our cognitive measures. In our shock condition, we observed whole body discomfort, but there were a lack of statistical significant effects in the remaining variables. And this may be due to different anticipatory strategies that individuals employ due to sudden perturbations. With the high condition, not only did we observe whole body discomfort, but increases in reported headache, postural imbalance, and the decrement in vigilance was clear. So just to summarize, we found that whole body vibration didn't really induce additional effects beyond that seen for sitting without vibration. And this was due to the lack of statistical differences between conditions. and therefore whole body vibration may not necessarily be the only source of acute sensory-motor or cognitive effects. But what we observed was that with increasing vibration intensity, the pre-post effect also increased. So in terms of the current guidelines intended for long-term health outcomes, they may not be sufficiently protective when it comes to acute effects. So we're reminded by a quote from Michael Griffin in 2003, who stated when it comes to vibration guidance or guidelines, he stated that the quantitative guidance is really insufficient to identify vibration hazards, but really the qualitative guidance, i.e. reducing the risk to a minimum, that's the key message. So when it comes to mitigating possible vibration risks, you might be familiar with the hierarchy of controls, where the control solutions range in both their effectiveness as well as the feasibility of its implementation. So the most effective control strategy is to eliminate the hazard, but this often tends to be costly, especially if you were to implement this as a retrofit. On the other hand, personal protective equipment is easy to implement but less effective. So when it comes to controlling for excessive vibration, although we found from Bronson's study that active suspension seats were effective in reducing vibration exposure, these engineering controls are often expensive and they don't really address the potential effects of prolonged sitting. We might want to consider administrative controls in addition to these engineering controls, such as optimizing work scheduling and arrangement of tasks. And this may be feasible in non-routine jobs such as construction, where the scheduling of tasks may be at the discretion of the worker. So on the right from a previous study, we have 16 residential plumbers in their tasks that were completed over workday, morning and afternoon, and over a 5-day work week. So each row here represents a particular participant. The colored boxes themselves represent a different task. And what we find here is that tasks not only vary between individuals, so between rows, but also between workdays and even within a workday on a per participant basis. So this might afford us the opportunity to explore whether there's an optimal work scheduling arrangement to minimize the effects of vibration, but also further research on the cumulative effects and complex interaction of not only vibration, but other work demands involved in that job, be it physical or mental, particularly when these demands are performed sequentially. So just as a teaser, we do have a study that was published in PLOS ONE that demonstrates that different demands, when combined sequentially, are not necessarily additive, and in fact might introduce increased task variation. But what remains unknown are the optimal task ratios and whether short-term benefits might translate to improved health in the longer term. So at this time, both Bronson and I would like to thank our funding sources, as well as WWDPI and CREAMSD, and our respective institutions, and of course, our participants. If you're interested in further publications in which this presentation was derived from, those are found here on this slide. Thank you.
Hey, thanks so much, Marcus. Thanks, Marcus and Bronson, for a great presentation. We do have about 15 minutes for questions, so right now you can type in your questions and I will see them and read them out to everybody. So I have a question to begin with. Marcus and Bronson, it seems like the existing standards are working partially, but it seems for some outcomes they may not be working so well. Is there some thought into revising these standards right now?
Yeah, I think there's an opportunity. Although I believe there much needed research should be conducted in terms of the exposure response relationships when it comes to vibration exposure and these potential acute effects. I think going back to Michael Griffin's statement about the utility of the guidance in terms of its qualitative approach, in terms of reducing the risk to the minimum, I think that should be kept in mind more so than perhaps the quantitative guidance. When in fact that quantitative guidance might not necessarily indicate that if you're right below this particular value that you're absent of risk. So I believe in order for the development of good, sound guidance and standards we were to address acute effects. I think there should be a more research on these response dose relationships.
Fair enough. Fair enough. Thanks, Marcus.
Yeah.
We have a question that has come in from the group here. What kind of intensity do we see in construction workers in terms of whole body vibration?
Yeah, I'm just scrolling up to our second slide here, and there's a really clever study by Can in 2003, and they've been able to document some of the exposures of whole body vibration from multiple different types of machinery found in construction work. And just to reiterate, these values are, again, very similar to what you would find in terms of other machinery in other industries, but like other industries as well, a proportion of individuals are above standards, current standards in terms of long-term health risks. So in terms of exposures among construction workers, I think there is some transferability with some of the findings that we observed, since we are looking at vibration magnitudes within that similar range.
Okay, excellent, thanks. Another question is regarding maybe for both you and Bronson. What studies are you planning next in this area?
So from my end, definitely we evaluated vibration in terms of its intensity. But of course, there's other parameters of vibration that might be related or might affect both acute effects or the sensory motor properties, as well as potential risk factors for long-term health, and those being frequency and duration. So I think looking at these other parameters in addition to intensity, we can then start developing better models to understand the exposure response dose relationship before we can perhaps and hopefully develop better guidelines and standards.
Yeah, fair enough. And I mean, it sounds like actually, Bronson went through the mechanisms, and it seems there's you've got the vigilance, you've got balance that seems to be impacted, but there's also that long-term effects too, the nutrition and stuff like that that's happening. So, and really, you don't really have much for the long term in these things either, right?
There's like FE studies and like lab studies like with vibration with the spine and how it affects like passive stiffness. And there's FE studies with the mechanisms. But we also looked at like possible mechanisms or theories with how whole body vibration could affect alertness, is like the attention capacity theory, where like you have a certain capacity for attention, and if you're directing some attention to vibration, then you have less attention for other things. So yeah.
So it's coming, that stuff, but still not enough to change exposure guidance levels for these things, right? We're not seeing kind of thresholds right yet. Mm-hmm. Okay, we have another question in here in terms of a whole body vibration. What about the use of these anti-vibration seats, the electronically active vibration canceling seats? How much does it cost for one of those seats?
If you're looking for one, it'll be more. It's about like $3,000 for one.
Right. And do you see, I guess, I don't know if you guys know, is anything happening in construction? There's some uptake in the transportation sector, anything and some in mining, I guess. And I'm not sure how much is happening in construction in terms of people actually purchasing those things.
Yeah, I'm not sure about purchasing. There's people like the manufacturer has sold this technology to another company called Clear Motion now, and it looks like there's seats for agriculture and heavy duty pickups as well. So So it's coming, but it's not there yet. So it's only available for trucks right now.
So, okay, fair enough, Bronson, thank you. Another question is, would whole body vibration exposure for tow truck drivers be equal or greater than truck drivers in general? So tow truck drivers.
The EU Good Practice Guide, I think we're on that slide currently.
Yeah.
They do have some interesting ranges of some example machinery, including tow tractors and other heavy machinery possibly involved in construction. I think in terms of the long haul truck drivers, since environmental are key factors, and often they're driving on smoother and more refined pavement, I think we expect lower accelerations and lower vibrations amongst this population. And I think that's an interesting point, because the observations that Bronson had in terms of workday and multiple workday effects, this is from a population, again, with lower acceleration levels. So it might actually underestimate potential effects in accelerations and vibrations found in heavy machinery, where we observe higher accelerations. So it's kind of intriguing to me, at least, when it comes to Bronson's study, that we observe these effects even amongst a population with lower vibration exposures.
Yeah.
Good point, Marcus.
And I think it depends on like how far you're towing the tow truck is driving to too. So like the intensities are averaged for or standardized for 8 hours, but it really depends like how long you're driving for. So yeah, it's tough to say.
Yeah, and so I guess the issue with the long haul truck drivers is they're really forced to drive 13 hours a day to make money. So, and tow truck drivers they get out of their tow truck sometimes and do some other tasks, probably more often than these long haul drivers do. So, so if anybody has any questions, feel free to type in. We have 5 more minutes here. I have another question though for our two presenters. You know, when I'm thinking about the regulations and the standards, I'm wondering about your thought on this. This is kind of different, but you know, typically for whole body vibration, we talk about you know, back problems and all the epidemiology, you know, about some of those issues on the back as being the critical health effect that drives the standard, right? And so now we're finding relatively new that you have this issue of vigilance and fatigue, right? That you see in all these studies. And I'm wondering if what you thought about. Well, the facts are is that you know, for some occupations, vigilance is not that critical, but some occupations it's a critical effect for performance. Would it be useful to have a different standard based on vigilance for some jobs? That's a tough question, right? Sorry.
Yeah.
As opposed to a blanketed approach for all jobs. So for instance, the current long-term health guidance is really a blanketed approach for all industries. Is that your question, Phil? Whether it should be industry specific, or whether guidance and guidelines should be, or whether they should be more of a blanketed approach?
Well, I think the problem with the blanketed approach is your long-term effects don't include things where if you have a vigilance critical job, you know, the outcome of that is a crash or a big accident where, sure, you're not going to have chronic low back pain after 30 years of exposure, but that's not really the critical effect for these particular jobs, right? So you're you know, I guess the former one is you know, should there be something said for people with these safety sensitive jobs that need to be vigilant and when you expose them to vibration?
Well, you know, Phil, but since a lot of individuals who are exposed to vibration tend to be operating heavy machinery and where safety is of utmost importance, I would imagine that in these sort of occupations, vigilance is a major concern. And if there's some fatigue occurring or some sort of ill-performing factors that might be involved, it can have serious consequences, such as crashes and even potential egress issues when coming out of the cab of the vehicle. But I think, having said that, I think a lot of these vibration exposure occupations and jobs, safety is critical amongst a good majority of them, since they are operating vehicles and heavy machinery.
Good point, Marcus. Yeah, you wouldn't be doing that if it wasn't a safety sensitive too, right? Good point.
And I think we need to get the technology there to be able to reduce vibration to that certain level first. Just looking at the EU good practice, like we're still trying to get the technology to be able to reduce vibration. So I think there needs to be more work done in that as well.
Yeah. Okay. Any final comments from Bronson and Marcus? Because we only have 2 minutes left here, and then we got to sign off. And thanks for the audience out there for signing up here and listening. Hopefully you gained a lot of information. I know I did, so it was great. But some last points, you guys?
Well, I guess in terms of vibration exposure, again, the key message: reduce your vibration as much as you can, and definitely use the current guideline thresholds as kind of a targeted value, but knowing that there's still potential effects beyond that, or effects related to more acute sensory motor or cognitive changes. That's still a possibility at these levels. So reduce the vibration intensity as much as you can. That's the main takeaway.
Great. Thanks, Marcus.
Thank you, Marcus and Bronson, for your presentation, and thank you, Philip, for moderating this webinar. To our audience, thank you for joining us.